Sally is an artist who recently launched her very first online store. To protect her customers and their login data from automated brute force attacks, she installed a popular security feature on her login page, a CAPTCHA. CAPTCHAs operate on a specific assumption. By asking a user to read distorted, squiggly text, they act as a digital bouncer. The logic is that humans can easily parse those wavy numbers, but machines cannot. But visual barriers are rarely impenetrable. To test this system, an ethical hacker named Kim was hired to probe Sally's login form and look for flaws before real attackers do. Relying solely on a visual test creates a false sense of safety. As Kim is about to demonstrate, modern automation can bypass these checks entirely. Kim's strategy revolves around building a custom Python script. Layer by layer, he writes code that interacts with the website, reads the target images, and automates the login process. To see how a digital defense mechanism falls apart, we have to deconstruct how an attacker programs a machine to mimic human vision and persistence. The attack starts with web infrastructure. Kim imports a Python library called requests. This tool allows his script to act like a real, persistent web browser. It holds onto cookies and session IDs, which is essential for maintaining a continuous connection with Sally's site. This flow architecture illustrates how a CAPTCHA actually works. It is rarely a static image hard-coded onto the page. Instead, it is a dynamic server endpoint. Every single time a user or a script visits that specific URL, the server generates a fresh code on the fly and returns a newly generated graphic. Once the server sends that fresh graphic back, it arrives as raw binary data. Kim uses two more Python libraries, IO and Pillow, to catch that stream of bytes and convert it into a workable image file on his local machine. By utilizing these libraries, Kim's script bypasses the traditional web browser entirely. He is now directly talking to the site's underlying architecture, fetching the exact images he needs. Now that the script can download the images, it needs a way to read them. For this, Kim integrates CAPTCHA, an open-source optical character recognition engine. This serves as the script's visual cortex. This visual filter demonstrates the core concept of optical character recognition, or OCR. CAPTCHAs are intentionally filled with colored lines and chaotic noise, meant to confuse automated systems. An OCR engine systematically ignores that static, looking past the clutter to identify the stark, geometric shapes hidden underneath. Tesseract isolates those core shapes, recognizes them as numbers, and converts them into a clean string of text. If the image displays a messy 9312, Tesseract outputs a perfectly typed 9312 into the script. The bot now possesses programmatic human vision. The entire premise of the CAPTCHA, that only a living person can read the distorted digits, has been neutralized. With the visual barrier bypassed, the script requires a massive library of potential credentials to begin the brute force phase. Kim turns to SecLists, an open-source repository of leaked credentials used by researchers to simulate real-world attacks. From this database, Kim loads two highly targeted files into his script's memory, a short list of standard administrative usernames, and the best 15, a curated list of the most commonly leaked passwords globally. The bot is now fully prepared. It possesses the vision to read the screen and the data to test the password combinations used by millions of people every day. Kim faces one primary dilemma. Optical character recognition is imperfect, occasionally misreading the text. When a login fails, the script needs to know, was the problem a misread image or just a bad password? The answer comes directly from the target. Sally's server returns error messages that are highly descriptive, indicating exactly where the login process stopped. The server checks the CAPTCHA first. If wrong, it returns CAPTCHA failed. Kim uses this to restart, trying the same password with a new image. If correct, it checks credentials. Invalid password confirms the image was read, so the script tests the next credential. By trying to be user-friendly with specific, distinct error messages, the server has provided the attacker with a perfect, self-correcting roadmap. To tie it all together, Kim wraps his logic in a simple Python while-true loop. This forces the script to endlessly request and solve new CAPTCHAs until it achieves a perfect read for every password guess. The automated sprint begins. The script pulls an image, reads it, submits a password, and checks the response, burning through credentials at superhuman speed. Then, the loop breaks. The script submits the username admin and the password dragon. The server returns no error messages. The target is breached. Kim now holds total administrative control over the store's digital infrastructure. The effectiveness of a CAPTCHA relies entirely on the server logic behind it. When that logic reveals exactly why a request failed, it provides automation everything it needs to systematically dismantle the defense.